Hi everyone, my name is Yazid Merah. In this video, I will present our paper entitled Ontology-based cyber risk monitoring using cyber threat intelligence. This is a joint work with Tayeb Kenaza done in the Military Polytechnique School in Algeria. This paper presents an ontology using cyber threat intelligence to the scope of cyber risk monitoring. So let's start by talking about cyber threat intelligence, or CTI. CTI is a cybersecurity discipline that offers the opportunity to be proactive in the computer and network security area, and it is nourished by the traditional theory of intelligence. The objective of CTI is to know and understand cyber threats and adversaries by specifying their motivations, tactics, techniques, and procedures, vulnerability used, infrastructure, and victims. In summary, CTI offers the cyber operator how to keep up with hackers out, what threats are coming, what vulnerabilities are exploited, and what cyber attack patterns are occurring. Leveraging CTI information involves using standards. Structured Threat Information Expression STIX proposed by MITRE is a cyber threat modeling language that gains popularity with multiple tools and libraries developed by cybersecurity actors. STIX includes domain objects related to attack such as attack pattern, malware, intrusion set, campaign, tool. Others related to observed information such as vulnerability indicator and observed data. We can also find some domain objects related to users or organizations such as identity and threat actor. Additionally, STIX offers information about course of action and malware analysis, etc. In addition to those domain objects, STIX defines the relationships between these objects. These relations make it possible to describe or highlight links, for example, between malware and vulnerability used, or between malware and indicator or signature that can be used to detect it, etc. STIX allows us to build a kind of graph that is easier to interpret by humans, thanks to JSON language. This slide, extracted from the STIX website, shows a scenario of threat actor known as adversary Bravo. Characteristics and attributes of adversary Bravo, such as aliases, motivations for attacking, and roles they may have in an attack, can be modeled using the threat actor domain object. As shown, this actor uses Poison Ivy malware to establish a remote backdoor and perform nefarious activity. Adversary Bravo uses phishing as a delivery mechanism that can be represented using an attack pattern domain object. One other interesting concept that is seen in both malware and an attack pattern object is the ability to provide kill chain information. In this example, attack is associated with the kill chain phase initial compromise. Several organizations compile CTI information from many different sources such as social media, incident response reports, discussion groups, or the dark web. These organizations make CTI information available to cyber operators. We find on the internet some open source CTI platforms that provide this kind of information in STIX format. The most popular platforms are the Malware Information Sharing Platform, MISP, Alien Vault Open Threat Exchange, IBM X4 Exchange, National Vulnerability Database, and the MITRE Cyber Threat Intelligence Repository. This work aims to propose an ontology-based CTI to monitor cyber risk. By examining related work, we find some motivations which led to this paper. First, CTI data is generally not linked to cyber risk management and assessment processes. Secondly, several ontology-based initiatives have been proposed that address these two areas separately by targeting a single problem at a time. And finally, most of the proposed ontologies do not cover important CTI concepts, such as attacks, sources, target systems, exploit vulnerability, impacts, and mitigation measures. By examining the definition of cyber risk, Oleksky and Taras Kovalenko extracted the dependencies between the concepts of risks, threats, vulnerabilities, and information assets. As shown in Figure 1, cyber risk assessment is no longer just an arithmetic equation but rather a triple reasoning model. On the other hand, Kim and R emphasizes the importance of the correlation between security incidents and CTI's information. So correlating the security events with the information from the CTI improves cyber situation assessment. On this basis, by adding a real-time dimension represented by events that occur in a computer network, we obtain the diagram presented in Figure 2. This figure demonstrates the interest in our approach, where generally the strong dependence between security events and CTI is ignored or little taken into account in cyber risk monitoring. OntoSIM, proposed by Kenaza, is an ontology organized into 5 categories. Analyzers, it contains information about security tools used to protect the system, such as IDS, vulnerability scanner, firewall, integrity checker, etc. Events and alerts. Security tools trigger a message when an event occurs. There are several kinds of messages such as alerts. In general, these messages are well structured and formatted in XML. Attacks and vulnerabilities. Here we find concepts such as vulnerability, attack class, signature, and configuration. These later represent a collection of software that are vulnerable to a specific vulnerability. Topology and cartography. This category regroups information about assets of the system, users and attackers. It concerns information about the user's profiles and attacker intentions. OntoSIM is very suitable for event correlation when many security tools have to cooperate and exchange information. However, this ontology does not cover all CTE concepts. Several studies state that an efficient cybersecurity ontology should embed 6 concepts. Starting from this, we propose in this paper an extension of OntoSIM while integrating CTI based on sticks within an objective of cyber risk monitoring. For this purpose, we built an ontology by following a rigorous constructor methodology. This ontology was developed by taking into account the following objectives. Firstly, providing a detailed description of all important concepts related to CTI, events, and topology. And secondly, providing a detailed description of relationships between classes. According to OntoSIM, we identified the equivalent concepts with sticks such as threat actor, vulnerability, attack, and indicator. We also added some sticks concepts such as campaign, intrusion set, tool, course of action, identity, observed data. This figure presents the architecture to use our ontology. This architecture consists of 4 modules. The collection module gathers all security reports from CTI sources and analyzers. The parsing module retrieves security information by browsing XML and JSON reports, referring to the CTA data and the alerts reported by the analysts respectively. This module uses the JSON API for processing CTI files and the XML E3 element 3 API for security alerts to parse XML files. By using our ready-to API, the populating module feeds our ontology with concepts, their properties, and relationships provided by the parsing module. Finally, the reasoning module runs rules which are carried out with the semantic query enhanced web rule language tool and gives us an answer to monitoring questions. To demonstrate the validity of our ontology, we used a platform that includes some nodes as shown in this figure. In this test environment, some unpatched operating system and software are deliberately installed to get vulnerable nodes. We also use the OpenVAS vulnerability scanner that provides information about vulnerabilities, hosts, software installed, and much further. This tool has reported 221 alerts involving 49 vulnerabilities. Then we export result in an XML file to populate our ontology. To get CTI data, we built a CTI dataset from several open CTI platforms. After populating the proposed ontology with OpenVAS report alerts, we search into the CTI dataset for all reports related to the vulnerabilities discovered. These found CTI reports are parsed to extract sticks information, which was also populated on the ontology and linked to related vulnerabilities with relation check. Cybersecurity decision makers through our ontology can get an overview of cyber threats and develop robust solutions. Indeed, this can be provided by answering a set of questions. For example, we might be interested in the following issues. What are the most dangerous vulnerabilities in my network? What are the threats that could exploit the discovered vulnerability? What attack patterns used by the identified threats? What are the user's privileges required for a specific threat? What are the aliases of the identified threats? Are there calls of action to reduce or eliminate the identified threat? What are the preconditions that have to be satisfied for an attack? To answer these questions, we propose rules that express some security objectives to be monitored. To illustrate the usefulness of our ontology, we give an interesting example that follows a specific vulnerability. Now let's take a look at the CVE 2017-0144 that targets Windows operating systems. So we want to know what threats reported in CTI can exploit this vulnerability. Rule 2 gives this kind of knowledge by searching all classes that target this vulnerability. By referring to sticks relationships, we can see that threat actor can exploit this vulnerability. In addition, malware, attack pattern, and the Trojan set that are subclasses of attack used to this vulnerability. By running this rule, we identified 6 malware, 4 intrusion sets, 6 tools, and 1 attack pattern as shown in this table. A cyber operator is constantly confronted with threats. To better anticipate, it is important to have a set of recommendations or actions to take in case of a computer attack. As shown in this figure, the course of action mitigates the impact of the attack pattern identified for WannaCry malware. The above rule gives the later courses of action deducted from the CTI that can be employed against WannaCry to reduce the attack surface. The courses of action identified to mitigate the impact of WannaCry are data backup and data encrypted for impact mitigation as shown in the table. We have proposed in this paper CTI-based ontology to monitor cyber risk. This contribution is an extension of Ontology proposed by Kenaza. The strength of this ontology is the inclusion of security events reported by different analyzers and the information from the CTI. We implemented our ontology in R, and its usefulness is demonstrated through an application. A set of reasoning rules have also been introduced to monitor cyber risk proactively. This proposal can be considered as a decision support tool in the field of cybersecurity. Nevertheless, the proposed methodology must be completed by other concepts to give more capabilities, such as security metrics to assess cyber risk. Finally, we need to develop new approaches to get more trusted and highly accurate CTI.